Okay, so the last two sections we're going to look at for this week are 3.7 and 4.1. So we've done a lot of graphing two equations on the screen and seeing where they intersect. Right? So that's basically what this section is about. I think most of the time that we've done it, you've only had to solve for two variables. And that's because if you're going to graph it, our calculators only graph in 2D. If you wanted to do a third variable, you'd have to be able to draw in 3D. Okay, and our calculators don't really do that. There are apps online you can do it with, but we're going to pretty much stick with solving two equations for two variables. Okay? But you can have more. We just start to get away from a graphical approach at that point. Especially if you get into like 4 equations or 4 variables, now you're talking about drawing in something we can't even imagine. Because if 3 variables is like a 3D, 4 variables, you're drawing in 4D. So now sketching doesn't even make sense. So if we're solving a system with 2 variables as the answer, you have to give me an x and a y value, and you can write it as an ordered pair. You could also write the answers separate, like x equals 4, y equals 5. Or just write it as a 4, 5 in parentheses. Either way. So remember, what we're looking for is points of intersection. Now, in order to be able to type a system into the calculator and graph it, what has to happen first? You can only type an equation in on the calculator if what? Yeah, we basically, something equals. What do we have to get it equal to? Usually 0 if we're going to factor it. But if we're not factoring, we're going to get it equal to y. You've got to get the y by itself. And there are equations where that would be impossible. Okay, I could give you one that you can't get y by itself. Like they've actually proven you can't do it. If I gave you something like this. E is, it's like the number 2.718. It's like pi. I think we might have talked about it. If not, we will when we do logarithms, in chapter 5. But you can't get y by itself easily here. If you didn't have this y, then that would be easy. Just subtract e from each side and you're done. If you didn't have this y, you could also get it by itself using what's called a logarithm. But the problem is you have both of them, so there's no way you can get y by itself in that equation. Can't do it. So graphing would not work for this approach if you wanted to graph it on a calculator. All right. So let's see if we can solve this system graphically. Okay, if somebody gave me that and didn't say how to solve it, I would probably just go with elimination. But they want us to graph it, so let's try that. Okay. To Derek in the top equation, what do I have to do to get y by itself?
Top equation, you subtract 2x from both sides and you divide by 3.
And what is going to be divided by 3? You said divide by 3, like
yeah. And you divide by 3 from both sides too.
On both sides, so everything. So you're going to divide by 3 in all 3 spots. So that's going to give us negative, just double check me on that. We're going to have a negative 2x, then you divide by 3, and you're going to have a positive 5 divided by 3. Questions on that one? Okay, so now that one's ready to type in. How about the bottom one? Can someone solve for y there? Yep. Okay.
You add 3x to both sides and divide by 5.
Add 3x and divide by 5. So that's going to become a positive 3x. When you divide 3 by 5, you get 3/5 for your slope, plus a y-intercept of 21/5. Okay. Now we'll plug them in and see what we get. So we've got, I would use, well, there's two ways you can do it. You can either use parentheses, or you actually can get away without using parentheses if you did it like this. Negative 2x divided by 3. That's the same as negative 2/3 x. Okay, the x is in the top. Now, I'm not sure if you would need parentheses around the 5/3 though, because I don't want the 5/3 to be added to the 3 denominator. So I'm going to do plus. And then in parentheses, I do plus. I'm going to do plus. No, not again. I don't know why it randomly does that. Okay, let's try now. Plus. Okay, 5/3. Okay, I think that would be okay. I don't really like it because I'm a little nervous about the parenthesis thing, but I think order of operations, it would do the division before it does the multiplication, so it should be okay.
So on the top, if you did it in like normal in parentheses, would it be negative 2/3 x in parentheses?
Yeah, I'll do the bottom one like that.
Okay.
So you could do 3/5, I should have put a parenthesis, and then put the x next to it, plus 21/5. Okay. If somebody did the top one like that, you can let me know if it comes out the same. I might have to change my window, but no, it's okay. I can see the intersection. Right, so let me do second calc intersect. Well, I got a nice answer, so probably the top one was okay. Anyone else get negative 2, 3? Okay, then we're probably okay. It's kind of a tough one to check. But if you plug in negative 2 here, you get negative 4/3 plus 5/3. That would give me negative 4/3 plus 5/3. Oh, 9/3. Yeah, okay. 9/3, which is 3. So it did work in the top. If I plug negative 2 in the bottom, I get negative 6/5 plus 21/5. So negative 6 plus 21 gives me 15/5, which is 3. Yeah, so it does work.
I got the same without parentheses.
Okay, yep. So I put them in, but again, there's multiple ways you could write it. Okay, any questions on that one? So 2 linear equations, there's only 3 things that can happen. They're parallel, they're the same line, or they cross in one spot. When we start to look at equations that have cubes and squares and all kinds of other things, now we can have a lot more twists and turns. So this would be pretty hard to solve by hand unless it had a rational root and you could use synthetic division. Because what you could try is substitution. You could plug that in if they didn't say to do it graphically. Set it equal, and then put everything on one side, and then hope that you can find a rational root. Divide through at least by one of them to knock this cubic down to a quadratic. All right. But the focus of this section isn't really on finding roots with the rational root theorem. It's more on the graphing. So let's take a look at it. So we've got negative x cubed plus 3x squared plus x minus 3. And then we got negative 2x squared plus 5. Okay, I'm going to go back to a normal negative 10 to 10 window. And I want to know how many times they cross and where they cross. Okay, so how many solutions am I going to get? 2?
3.
3? Let me see 2. Let me see 2.
Wait. 3 could be there.
Could you go down?
3.
All right, let's go down. See what happens. Let's go down to like negative 40. The other 2 are going to be harder to see now because they're going to be a little more squished in the top of the screen. But I think you'll still see them. Oh yeah.
Yeah.
So we are going to get a third one. I can't tell if they've reached the intersection yet. If the intersection is off the screen, I don't think you can calculate it. Pretty sure you can't. So if you go to -60, I'm thinking now it'll definitely be on the screen. So we get 1, 2, yeah, we got 3. So that's something you have to keep in mind. Okay, you may have intersection points that go off the screen. Right? How do you know that? You're just going to zoom out and see what's going on. So, second calc intersect. Okay, I'll do the 2 at the top. If someone else can do the one that's way down, that'll save us time. Okay, so there's our first one, which I'm just going to shrink a little bit. All set? Okay. There's one. Okay, second one, second calc intersect. All I have to do is move the guess a little closer, and it should give me this one. Yep, there's the second one. So 1, 2, and the third one I'll just write by hand. What do you get for the third one?
X equals 4.867816.
So 4.867?
Yeah.
Or 4.868?
67.
Oh, it does round down, okay.
Oh wait, no, it does round up.
Yeah, around those.
It rounds up. It's 4.867816. So it's not
And then the y value is probably like -40,
negative 42.
42.39. Okay.
Does it round down or round?
So there is no quick way to do that. Some calculators can give you all the intersections at the same time. That'd be handy. But we got to do each one separate. Okay. So any questions on that? Notice here, there's no nice answers. I don't think any of these x values can be written as fractions. I mean, maybe they can, but I don't recognize 0.3497647 as a fraction. I'm not sure what that would be. It's kind of close to like a third, but it's not 0.3, it's 0.34, so that's probably the best way to do it. Okay, any questions on that one?
So that's how you would write your final answer, like.
Yeah, I would actually, on the test, you're not going to be able to drag the graph,
Right.
obviously. So I would just write this 3 times.
Okay. As
Three.
all the solutions.
Yep, circle each one separate. Yep.
Could you just do ordered pairs too?
You could also just do ordered pairs. Yep. Okay, so this one says graphically and algebraically. You know, if they say algebraically, something special must happen to make it easier. So I'm going to do algebraically first. What method here would be the best? Substitution? Elimination? If you're going to use algebra.
Substitution.
Substitution. They're both solved for y. So let's replace y in the top equation with 3x. And I'm guessing we can probably do this with a GCF in a minute. What do you want to get it equal to if you're going to factor it? 0. 0. So we're going to get x cubed minus 4x. And now what's the GCF?
1.
There's one bigger than 1.
2.
No.
1x.
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 Because this is a 1 and a 4, so the GCF of 1 and 4 is just 1. But they both have an x in common. What do you get in the parentheses?
X squared.
Which is a difference of 2 squares, so that factors. I think we did that in the homework. What does x squared minus 4 factor as?
X plus 2 minus 2.
Yep. So how many roots does this equation have?
3.
3. And they're all what kind of roots?
Real.
They're all real. So the roots are
0.
so actually, we gotta be careful. There's 2 things we have to do. So 0, -2, and +2. But I'm only half done. What else do I need? I need the y's. So these are the x's. Now let's write the 3 y values for each one. simplest way to get the y value is just triple the x.
Oh, cool.
Okay? Triple the x. So if you triple 0,
0,
you triple -2,
-6,
and +2,
6.
and that's okay.
You can do that?
You could write your answer like that, and I would understand that, and that are the answer. Or if you want to do coordinates, you could do this too. As long as you write it in a way that's clear and I can tell what the roots are. Most people just do coordinates. Okay. So any question on doing that algebraically? Yeah.
Where did the 6 come from?
So to get the y value, you take your x's and triple them. I mean, you can also do this, but this is easier. So we just tripled each x value.
Or you could just graph it and see that.
Yes. Is there any question on how you would do it graphically? Graphically would be just like one of these problems. Except you're going to get all nice answers here. Okay. Just calculate all the intersection points. I don't think none of these are off the screen. So you're going to see -2s and 6s all in a standard range. Okay. Okay. That's really it for 3.7. All right. So 4.1. It says rational functions. Pretty much the focus of all of chapter 4 is rational functions. What does rational mean again? Yeah?
It can be represented as a function.
Represented as a what?
Like, what is a function? As a fraction.
Fraction, yes. So we're dealing with functions that are fractions. Okay? That's what we're going to be looking at. So with polynomials, we never really had to worry about dividing by 0 or anything like that because polynomials don't have fractions with variables in the bottom. These will. Okay? And whenever you have a variable in the bottom, that can happen. Okay? And we've seen that when we talked about continuity. Like we had pick up our pencil and put it down somewhere else if we had a graph that divided by 0. We never called it a rational function, but something like this, that's a rational function. It's a polynomial in the top and a polynomial in the bottom. And that's exactly what I write right here. So rational functions are of the form p of x over q of x. P of x and q of x are just two different polynomials. Okay, so you could have something like x squared plus 3x plus 7 in the top, and in the bottom, x minus 4. Okay, just two polynomials divided. The only thing that q of x can't be is 0. Why not?
Because you can't divide by 0.
Yeah, you can't divide by zeros. So q of x cannot equal 0. So there's an example of a rational function. I don't think I'm actually going to do anything with it. I'm just showing you an example rational function. Maybe later we will, but I don't think I do anything with it yet. No. So it's an example, not an example to solve, just an example of what a rational function looks like. X squared plus 1 over x minus 3. And here's another rational function. 3x squared minus 4x plus 1 divided by x squared plus x minus 2. And the book has a lot more examples. So any question on what a rational function is? Just a fraction of two polynomials. So, the domain of rational functions. Now we have a fraction. What are you not allowed, I kind of already asked this a different way, but what are you not allowed to do? You can't divide by 0. So the domain is every real value, all reals, except any values that would make the bottom 0. And how do we figure out the values that would make the denominator 0? Well, you set the bottom equal to 0, and solve it. That's what we basically did in the whole last chapter. Find the roots of the denominator. Okay? If you can find the roots, then you just figured out the values that make the bottom 0. Usually the roots, it's not going to be as complicated as like having to use synthetic division and all that. Most of the time, you can either just look at it and say, oh, the root in the bottom is 3. Or it might be a quadratic that's factorable, and you find the roots that. Okay? Very rarely you're going to have to use quadratic formula, because then the problems start to just get kind of involved. It take a long time. Yeah, Adriana?
So if x can be like all real numbers, then what if x is an irrational? Is it still a rational function?
Yes, the function itself is still rational. It doesn't mean when you plug a number in that the y value comes out rational. Does that make sense? So when we call something rational, we're not saying that the answer from it is rational. We're saying that that thing itself is rational. But depending on what you plug in, it could change what kind of answer you get. Yeah. Okay, so let's find the domain of A. What's the domain there? All real numbers except for 3. So you could write that out, all real numbers except for 3. Or we could say negative infinity up to, not including 3, or 3, not including it, up to infinity. Any questions on how I wrote it that way? Okay. Or you could write all real numbers except when x is not equal to 3. All reals not equal to 3, however you want to say it. Okay, let's look at this one. Why are the values that make the denominator 0 a little harder to find this time?
I think that's 1. Except 1. And
Well, how come this is taking longer? Right, because it's a higher degree. It's a quadratic, okay? So we got to factor it or use the quadratic formula, okay? When we're looking for values that make the denominator 0, we're not interested in imaginaries. No imaginaries. We're only looking for real numbers that would make the bottom 0. And I agree, 1 is going to be one of them. So let's factor it. Not worried about the top. So if I know 1 is a root, just because I checked it in my head, I know x minus 1 is a factor. And what's the other factor? Let's check it. X squared plus 2x minus x. Perfect. So, what is the domain here?
Anything that doesn't equal 1 or negative 2.
So all reals except what? 1 and negative 2. So you can write it that way. Or you can say any number from negative infinity up to, not including negative 2. Or you can pick anything from negative 2 to 1, not including negative 2 or 1. Or 1 to infinity. Those are exactly the same thing. Any questions on writing it either way? Especially if it's a multiple choice question. You don't know how they're going to write it. So you got to understand both. Okay. C. Actually, I think C is easier than B. What's the domain here?
All reals except for 2 and negative 4.
And I'm just going to write it that way. All reals except 2 and negative 4. So 1 stuck easier than B because it was a quadratic, but they already factored it for you. I would say most of the time you're going to have to factor it yourself.
But it shouldn't be one where we have to use a quadratic formula.
I won't say you won't ever have one like that, but most of them are going to be factorable because it kind of speeds things up.
Right.
All right, so the simplest rational function you can have is called the reciprocal function. This is the simplest one. It's just 1 divided by x. 1 is technically a polynomial. It's what we call a constant polynomial. The bottom here is a linear polynomial. Okay, it's a degree 1. It's a degree 0 divided by a degree 1. Let's just graph it and see what it looks like. So 1 divided by x. I'm going to do zoom 6. Okay, now that's kind of what it should look like. Anybody remember what I've said about, we may have seen this one before?
Yeah.
It's not a completely accurate picture. How come? Yeah?
It stops on the y-axis.
It looks like it stops, right? It shouldn't. Okay? It's just once things start getting really steep, the calculator freaks out. So this should keep going up. This should keep going down. Left and right looks pretty accurate, except the screen runs out of resolution and it looks like the graph is actually coming down and going right on top of the axis. It never does. None of the axes here are ever harmed in any way by the rational function. They're never touched. Okay? They just get closer, but they don't ever reach it. If that makes sense. Okay? And now we're going to get into defining what an asymptote is. Okay? So, as x heads farther and farther to the right, or farther and farther to the left, what's happening to my y value? It's getting closer to 0 on both the left and the right. On the right, it's coming down towards 0. On the left, it's coming up towards 0. But in both cases, the y value is approaching 0. So, if we were to graph the line y equals 0, okay, if we graph y equals and the value that we're approaching, what we get is a horizontal asymptote. Okay, so horizontal asymptote is basically a line that I could draw, maybe. So it's a line that I can draw in my graph that something gets closer and closer to but never actually reaches. Okay. If you go to the table, if you try going to the table, let's run this. It's a bad day for the calculator. You go to the table and you type in second table. Type in a value like 25. I don't know if you can really read it, but it says 0.04. It's getting closer and closer to 0. If I go all the way to 100, it would be even smaller. Okay? But the point is, it's never actually reaching, it's never going to reach 0. Let's see if I can try typing in. Yeah, that works. All right. So that's an asymptote. It's just a value that you get close to but never reach. To find horizontal asymptotes, this is how you do it. You examine what's happening to the y value as x gets really, really, really big, like a really big positive number, or as x gets really, really, really negative. Okay? And when I say when x approaches infinity, you can probably just go to the table and type in a number, did it again. Type in a number like 100, and that's probably big enough to tell you what the asymptote is going to be. Okay. Eventually, remember, it's going to just say 0 in this column, because the calculator is going to round it off. Okay, but it never really reaches 0. These are both examples of graphs that have horizontal asymptotes. The one on the left is kind of like the one we looked at. The one on the right is a little different. I didn't say that when you have an asymptote, your graph never crosses it. I just said as you head very far to the right or the left, there's a value that you're getting closer to. And in the graph on the right, you cross the asymptote very early on, but then later the graph just continues to get closer and closer and closer. We also have one, I think they show one in your book like this, a graph that does something like this. Technically, that's considered an asymptote too, because as you head further and further to the right, your graph is basically converging to a value. It's getting closer and closer. This one constantly oscillating above and below it. One like this, just constantly approaching it. Okay, but as long as you're approaching a value, that's an asymptote. So, let's see if we can find the horizontal asymptotes of this graph. Now, all we have to do in our head is pretend like x is getting really, really big and see what this expression gets closer and closer to. Now, if x is 100, what's 1 divided by 100? What is it?
0.01.
0.01 plus 2. 2.01. So very, very close to 2. If you let x be 1,000, you're going to have 1/1000th, 0.001 plus 2. That's 2.00001. So this graph is getting extremely close to 2. And that is your horizontal asymptote. If you plug in -100 for x, you would have 1 divided by -100. That's -0.01 plus 2 is 1.99. So that's still very, very close to 2, no matter which way you head on the x-axis. That's the asymptote. Yep.
So wouldn't it just be like your y-intercept? Like looking at the problem like right away, wouldn't you know that it would just be 2? That's getting very close to.
So you're saying if you draw this, it's going to cross the y-axis at 2?
Well, no. I mean, like just like looking at that problem right there, like wouldn't you just know that the horizontal asymptote is 2?
Yeah, because anytime I see a fraction with a variable in the bottom, I know as the variable gets bigger, the fraction basically gets smaller.
Right.
So anytime a fraction with a variable in the bottom is there, you basically can just ignore it. This is going to approach 0.
Mm-hmm.
So you really don't even need it.
Yeah.
And the answer is just the vertical shift.
Right.
Mm-hmm. Even if I made this like a 12, doesn't matter. 12 divided by 1,000,000, 1 divided by 1,000,000. Basically the same number, 0.000 something.
Right.
Very small. So how about here? What's your horizontal asymptote? -3. This fraction is going to approach 0. Plug in a huge number for x. You're going to get 0.000 something. Okay? -3 is a number very, very close to -3. Either slightly above -3 or slightly below. Depends if you let x be positive or negative. I wonder if that's why, because I didn't put the other pen back. Well, I still might need to reset it. Okay, so your horizontal asymptote here is at -3, and the equation for it is y equals -3. I'm not going to worry about sketching it, because I kind of explained it, but if you basically take the graph of 1 over x, which I have right there, take each part, if you put a +2 on the end of a function, remember that's a vertical shift. +2, I don't know if I did it exactly +2, but that's what a +2 would do. It would shift everything up 2. All right? If you did a -3, it would take everything and move it down, like 1, 2, 3, like that. 1, 2, 3, I don't know, kind of like that. So putting a plus or a minus just shifts it up and down. Yeah.
What is the domain of that graph that you just did? Would it be like
The domain of this one?
the one that we just did over x? Wouldn't it be just all reals and 0?
Except 0, yes. All reals. And we're going to talk, well, I'll mention something in a second. Yeah, be all reals except 0. All right, so we did that. We're not doing that. Okay, so some functions can have 2 horizontal asymptotes. Okay, so we're going to look at one that has 2 right now. And the way we're going to do it, I just want to see what the problem is. Okay, we're going to break it into cases. Okay? Usually you have to do this when you have an absolute value. Because with absolute value, you usually have 2 possibilities. Right? You either have a number that's already positive, in which case absolute value does nothing to it. Or you have a number which is negative. Okay? And in that case, the absolute value changes the sign. So those are really the 2 cases that you look at. Okay, so we'll break it into cases, and then we'll use division. So they want us to show that this graph has 2 horizontal asymptotes.
Does that mean there's going to be like a space in the middle?
It could mean that, or it could mean something like this, where a graph is trapped between 2. Could be trapped. It's probably going to be trapped in there. I'm not sure. We'll see. All right. So first thing we want to do is basically look at the case when x is already a positive number, or 0. If x is already a positive number, or 0, what does absolute value do to it? Nothing. You don't even need it. All right? So if you already agree that we have a value that's bigger than 0, that would basically be your formula. You wouldn't need to take the absolute value of the x because it would already be positive. Okay. And now, that's not written the way we normally see rational functions. We usually have a number here. Okay. That's how we usually like to write it. Well, we can write this with a number as long as we do out the long division. Or we could use synthetic, but this is pretty basic. So let's do long division because we haven't practiced it in a while. All right, so we have x plus 3. And we're dividing that into x minus 2. All right, so how many times does x go into x? Once. That's going to be our number. So now we got the number. 1 times x. X. 1 times 3. And subtract. -5. That's my remainder. So remember how we can write this. You can write it as your number plus your remainder over your original denominator. Your quotient plus your remainder over the original denominator. Now, if I did plus negative, what could I really make this?
Minus.
I could just make it a minus. I just noticed that. Those two are exactly the same. Remainder plus, quotient plus remainder over original denominator. I think we did that a couple days ago. All right. So now we can look at what happens here. What happens to this fraction as x gets huge?
It gets smaller,
How small?
really small.
Can you tell me what it approaches? I need a number.
It gets close.
Let's do
I
it.
think it's close to 1.
This fraction? Well, let's plug in 1,000,000. What's 1,000,000 plus 3?
It It gets closer to 1 each time.
1,000,003. And what's 5 divided by 1,000,003, basically? Pretty close to 0, right? So this fraction that I circled is approaching 0. If you take 1 and subtract something that's basically 0, what do you get? Basically, you approach 1. Either a little above or a little below. Depends on if x is positive or negative. So this tells me as x gets huge here, you will approach 1. Now, in this case, let's look at what happened if x is less than 0. This part isn't affected, right? There's no absolute value there. But what would happen to a number if you give me a number that's less than 0 and I take the absolute value of it?
It's like you multiply it by -1.
Right, it's like the sign flips. So this formula would basically become that. If you give me a number less than 0, I would have to take the opposite of the number that you give me, and that would make it a positive. Okay? So like say you gave me x is -8. -8 turns into +8. And that's what the absolute value would effectively do. Change the sign of the number that you put in. Okay. Now if we do the long division there, I'm just going to save us doing that part out. You get -1 plus 1 over the original denominator, -x plus 3. So what does, I think I forgot a sign, -1 plus. What does this part on the right approach? That approaches 0, and if you take -1 and add a number very close to 0, you get -1. So this part has an asymptote at -1, the first part, +1. So it is trapped. If you were to graph it, it does end up looking like this. As you head to the right, okay, positive numbers, you're approaching a value of 1. So your graph does something like that. As you head left, your graph is approaching -1. It would look like that.
Wouldn't it be above it though? Because 1 plus whatever is going to be above that asymptote. And then -1.
So like, just pick a number. Like, let's do a number that's kind of easy. Like, I don't know. If we do, well, if I could graph it, I could show you. Oh, maybe I can graph now. So, if I type in this problem, x minus 2 over absolute value of x plus 3. So, x minus 2 divided by absolute value of x plus 3. But you don't want the plus 3 inside. Plus 3 outside. Okay, and do zoom 6. Well, it's not, my drawing's not. What's that red line? Oh, what's that red line? So your graph is trapped between 1 and -1.
Okay.
It's not the best window, but if you set it like, go like -3 to 3, that might look a little better to show you that it's trapped between those two. Also, the curve isn't quite as smooth as I drew it. It actually is a little sharper right there than I drew it, but it's trapped between -1 and 1. Yep. Okay, so a little weird because you get 2 horizontal asymptotes. Now, I want to look back at the first graph we did and see what happens as you get close to 0. We already know you can't plug in 0, right? If you try to fill in 0, then you're going to divide by 0. But let's just plug in very close. So what happens if I let x be like 0.01? What's 1 divided by 0.01? 10. Right? What about 0.0? Oh, never mind. I was going to ask you about 0.01. 1 divided by 1/100th is 100. So what's happening to the y value as x gets very, 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 very close to 0?
It's going up.
It's going up, okay? Or negative 0.0001, it's going down, right? So as x approaches 0 from the positive side, this is how you could write it. As you get closer and closer to 0, your y value goes up forever without stop. As you approach 0 from, this means from the negative side, or from the left. Okay? So as you get closer and closer and closer to 0 from the negative numbers, your y value goes down. And I gave you guys an example of plugging in, what did I plug in? Like negative 0.0001. And I got negative 10,000. So that means something. If you get closer and closer to a number, and all of a sudden your graph just starts to curve up extremely sharply, or down extremely sharp, what that means you have is a different kind of asymptote. That's a vertical asymptote. So horizontal asymptote, you look at what happens as you approach infinity or negative infinity. Vertical asymptote, you're usually looking at what happens as you approach a number. Specifically, the number that makes the denominator 0. That's the number you're looking at. And I think I write that in a second. So, x equals whatever number you think. In this case, it was 0. If, as you approach 0, from either the left or the right side, all of a sudden your graph curves up very sharply, or down. And it just keeps going forever. If that happens, it means you have a vertical asymptote. And vertical asymptotes is pretty much what we spent most of chapter 3 on. Find the zeros, or the roots of the denominator. If you can tell me where the denominator is 0, then you can find the vertical asymptotes. Okay, so that's important. Now, if you had a common factor, we've looked at that before, you end up with a small hole in the graph. Okay, in general, we're not going to really focus on that, because this chapter focuses more on asymptotes. But if you did have a common factor, that would be a hole, not an asymptote. Okay, and we looked at that when we did continuity. Okay. So remember, vertical asymptote is always x equals a number, horizontal, y equals. What's your vertical asymptote here? 2. Yep. So as you approach 2, all of a sudden your graph is going to curve very sharply. What's your vertical asymptote here?
3.
Would it be negative 4?
Negative 3. This minus 1 has nothing to do with it. This would affect a horizontal asymptote. This affects vertical. Okay? This minus 1, I could make it a minus 12, and it's still the same answer. X equals negative 3. All right, so last one, we got to do the last one. I'm not going to sketch. Skip that. All right, so the last one we're going to look at is a mixture problem. So we've kind of done this before, but it's going to be a much easier mixture problem than we've done because we're not going to write 2 equations, just 1. Now, just to kind of get you thinking about what you need to do, if I said you have 50 ounces of liquid and 35% of it is an acid solution, how would you figure out how much acid is actually sitting in front of you?
50 times 0.35.
Right. You take 50 times 0.35, which means that out of the 50 ounces in the container, only about 17 and a half of it is actually pure acid. The other 65% is water. That's what you really need to know to be able to do this problem. Okay. And the other thing you need to be able to know is how you figure out concentration. So, concentration is basically total acid or solution, whatever chemical you're working with, the total amount of acid over the total, substance, everything, whatever, the total, all of it mixed together. So it's the total acid divided by just the total you have in front of you. So, last example says we have X ounces of pure acid. And we're going to add that to a 50 ounce solution that already has 35% acid in it. So what we're going to add into it is pure 100% acid chemical. Okay. I want to write an equation for the graph of the concentration.
So total acid plus X over total substance.
Yep, so basically I want to do this. So look at my solution the way it is now. How much acid is in my solution before I do anything to it?
How much acid?
Right, I have a 50 ounce container in front of me of 35% acid.
17.5.
So right now there's 17.5. Plus, how much acid am I pouring into it?
X.
X. That's how much acid I will have over the total. How much liquid is sitting in front of me before I add anything to it?
50.
50.
Plus
Yeah,
X.
plus X.
And I'm plussing X. Yeah. That's a graph of your concentration. So let's graph it, and that'll be the last thing. 17.5 plus X divided by 50 plus X. Now, your concentration is going to be a decimal between 0 and 1. Will your concentration ever reach 1? No. Because, well, how come?
No matter how much acid you add, there's always going to be something else in there.
Right. Okay, no matter how much acid you add to it, you still can't get the concentration to 100%. Never, ever. So there's a graph of your concentration. Notice, the more acid you add, eventually it levels off and it doesn't really make much of a difference. It's kind of like if you've had 30 tests and you take a 31st test. Is that taking a 31st test really going to change your average that much if you've already had 30 other grades? Not really. At first it changes a lot, but then your average kind of levels off over time. Okay? So there's one in the homework, and we can go over one of those before the test tomorrow if we need to, because that's on the test. Okay, so the homework from page 207, it's just graphing and finding a couple intersections, so that part's pretty quick. And then page 222, it's those questions, but look at number 48. I wrote A and B. I think there's a part C. You don't have to do part C. Just parts A and B on 48. Okay, I will also be after school today for extra help. If anybody needs to come by, we'll finish anything up from last week.